In this section, we're going to talk about how to solve systems of linear equations in two variables. So we're still dealing with equations that when you graph them, they're lines, and we're still dealing with equations that use two variables, such as x and y. So we spent the last few sections learning how to handle linear equations, so all the different important forms like slope-intercept form, point-slope form, standard form, how to graph a line, and parallel lines, perpendicular lines, all those kinds of things. And now what we want to work up towards is how do you handle real world situations that are mathematically modeled by two or more linear equations. So we're not quite ready to do the story problem ones just yet, but that's coming up soon. So before we can talk about how to solve systems of linear equations in two variables, we need to know what a system of equations is. So mathematically, when we say a system of equations, we're talking about a set of two or more equations that involve the same variables. So what that means is you have multiple equations, and each equation might use x and y, but though that x and that y, they have to measure the exact same thing. So however many equations are in the system, if they all have an x in them, then that x is measuring the same exact thing. If they all have a y in them, that y is measuring the exact same thing. And then what we're specifically going to learn how to handle in this section is what are called linear systems. So it's a system of equations, but specifically it's a system involving two or more linear equations. So the equations, when you graph them, they're lines. And then even more specifically, our equations are just going to have two variables in them. So x and y, or whatever the two variables may be. X and y are the common ones. All right, so if you have a linear system that consists of two equations each with two variables, so two equations and two variables, then the solution to that particular type of system is any ordered pair that solves both the equations in the system. So for example, let's say we have x minus 2y equals 5 and 4x plus 3y equals 9. These are both linear equations. This x is the same x for both equations. This y is the same y for both equations. So the x and the y measure the same thing in both equations. So this is a linear system because they're both, if we graph both of these equations, they would be lines. And then I claim that 3 comma negative 1, that ordered pair, solves both equations. And since it solves both equations, that would be the solution to this system. So you're looking for any ordered pair that when you plug it into both equations, it solves both of them. So just so you don't have to take my word for it, let's go ahead and plug 3 comma negative 1 into each equation and see what happens. So if I plug 3 into the first equation, I get 3 minus 2 times, well, now we plug in the y coordinate, negative 1, equals 5. Well, that's absolutely true. 3 plus 2 is 5. So it does solve that first equation. And if I plug 3 in for x and negative 1 in for y for that second equation, I get 4 times 3 plus 3 times negative 1. Well, that's 12 minus 3, which is 9. That's true. So I plug that one ordered pair into both equations, and it solves both the equations. So this ordered pair is the solution to that system. So what we're going to learn is how did I know that 3 negative 1 was a solution? Where did I come up with that at? All right, so before we look at an example, let's make sure we understand everything that could happen here. So when you're solving a linear system involving two equations, each with two variables, three outcomes are possible. So most of the time, the more interesting ones for us are the ones that the system has one specific solution. So one ordered pair that solves both of them. So if a system has one solution, then what that tells us is the graphs of the equations would intersect, and then where they intersect is the solution. And then there's some vocab that goes with this. So this type of system that has one solution, we say this system is a consistent system. It's a little bit of vocab that you need to know. Well, not all systems have one solution. Some systems of linear equations with two variables have no solution whatsoever. So there isn't an ordered pair that actually solves both of them. Well, in that case, if you were to graph the equations in the system, they would not intersect. They'd be parallel. So there'd be no intersection point. That's why there's no solution. This kind of system is inconsistent. So this system is called an inconsistent system. So a consistent system has a solution. An inconsistent system does not have a solution. Well, it's also possible that the system of equations has an infinite number of solutions. Now, this is more rare, and they're not really that interesting, but they exist. So what this means is if you were to actually graph both of the equations, their lines, their graphs would overlap each other. They'd be on top of each other. Basically, they'd be the same line. So since one line is on top of the other line, any point on either line would be a solution, but they're the same line, so it would be the same coordinate. So any coordinate on the line would be a solution to the system. So that's why there's an infinite number of them, because there's an infinite number of ordered pairs on the graph of an equation, of a linear equation specifically. Well, since this type of system does actually have solutions, it has more than one, but it has solutions, it's still a consistent system. So consistent systems have solutions. In this case, though, since there's an infinite number of solutions, the two equations in the system are called dependent equations. So if there's one solution, we say the system is consistent. If there's an infinite number of solutions, we still say that system is a consistent system, but the equations are dependent. Basically, because one equation is the same equation as the other one, because when you graph it, you get basically the same line. The two lines are basically the same line. So we'll see an example of that here in a sec. All right. So what we want to be familiar with are three different ways we can solve these. So we'll add more later when you discuss matrices, but we're nowhere near that yet. So at this point in algebra, we want to be able to solve these kinds of systems using what's called elimination. Also, we want to be able to solve them using substitution. And then we also want to see how you could solve them by graphing. So three different ways. We're going to look at all three in this video. Okay, so let's look at the elimination method first. So the directions are to solve the following system. So we have 4x plus 3y equals 5 and 2x minus 5y equals negative 17. Notice both of the linear equations are in standard form. So for the elimination method, we want both equations in standard form. So this is one of the times that standard form is quite useful. So we have x and then y and then the constant on the other side of the equal sign. So that's a good thing. Now for the elimination method, basically what we want to have happen is we want to be able to add these two equations together, and when we do that, we want either the x's or the y's to be eliminated. That's why it's called the elimination method. So I want to be able to add the x's, the y's, and the constants together, and I want either the x's or the y's to disappear. I want them to be zero. I want them to be eliminated. So the way we do this is we're going to take this second equation and we're going to multiply it by negative 2. So I'm going to take negative 2 times the second equation, and let's see, we're going to get the first equation, I'm just going to leave it alone. But if I multiply the second equation by negative 2, I get negative 4x plus 10y equals 34. So negative 2 times negative 17 is positive 34. So now what I want to do is I want to add these two equations together. So you add the like terms. So it'd be 4x plus negative 4x is 0x. And then 3y plus 10y would be 13y. And 5 plus 34 is 39. And then we end up with just 13y equals 39. You divide both sides by 13, and we get a y coordinate of 3. So y is 3. So we now actually know one of the variable values. We know y is 3. So to get the x coordinate, we can just take this y coordinate and plug it into either one of the equations. So you can plug it into either one. So I typically would just plug it into the first one just because it doesn't really matter. So I usually just pick the first one. So we'd have 4x plus 3, and then now that we know y is 3, we can plug in a 3 equals 5, and then that gives us 4x plus 9 equals 5. So 4x, just subtract 9 from both sides, and we get x is negative 1. X is negative 1. So I now know that my solution, we know the x and y, so the solution is negative 1 comma 3. So that is the ordered pair that would solve both of these equations. Now a couple things to keep in mind. That ordered pair has to solve both equations. Okay, so negative 1 comma 3 solves both of the equations. You can always plug it in to convince yourself. So 4 times negative 1 is negative 4, and then 3 times 3 is 9. Negative 4 plus 9 is 5, so it solves the first one. And then if you plug in negative 1 to the second one, you get negative 2. Plug in a 3, you get negative 2 minus 15 equals negative 17. That's true also. So you can always, especially if on a test, feel free to, if you have time at the end of the test, plug in your coordinate and make sure it actually solves both. The other thing that you need to realize is since we got one solution, that tells me that the graphs of 4x plus 3y equals 5 and 2x minus 5y equals negative 17 intersect at negative 1 comma 3. So that coordinate is where those two graphs intersect. And we're actually going to see that here in a bit. We're just going to solve this exact same system the 3 different ways so you can see how either method gets you the same answer. So we just solved this system using the elimination method and got negative 1 comma 3. And we're going to see later how to do it with substitution method and then again how to do it by graphing. So we'll see that they actually intersect right there in a little bit. All right, so let's solve that exact same system but using substitution. So to make this easier, I've color-coded the equations so you can kind of follow along with what I'm doing and where and why. So we've got the same system. We already know the answer. We just did it a second ago. Let's see how we could get that same answer by using what's called the substitution method. So the substitution method, I mean, it's named that because we're going to substitute something in for something else. So basically, you need to pick one of the equations. So I'm going to pick the red one just because I want to. You could pick the blue one if you wanted, but I'm going to pick the red one. So I'm going to take the red equation, which is 4x plus 3y equals 5, and you need to solve this equation for one of the variables. So I'm going to solve it for y. Again, I'm just going to solve for y because I want to. You could solve for x. That'd be fine. Your work would be a little different, but I'm going to solve this for y. So I'm going to subtract 4x from both sides, and then I'm going to divide everything by 3. So we get negative 4/3 x plus 5/3. Now that we have this solved for y, we're going to take that and we're going to substitute it into the blue equation. So my blue equation is 2x minus 5y equals negative 17. But according to the red equation, y is supposed to be negative 4/3 x plus 5/3. So I'm going to take that and substitute it in for the y over here. So I'd have 2x minus 5, and then for y, I'm going to plug in negative 4/3 x plus 5/3, and then equals negative 17. So that's the substitution part. So this top equation, the one in red, I solved it for y, and then I plugged that in for y on the second equation, the blue one. And then now we're going to solve that equation for x. So I'm going to distribute negative 5. So negative 5 times negative 4 would be positive 20/3 x. Negative 5 times positive 5/3 would be 25/3. Then we're going to combine like terms. So 2 plus 20/3 would be 26/3 x. And then I'm going to subtract 25/3 to the other side. So negative 17 minus 25/3. And I'm going to get 26/3 x equals, now we got to get a common denominator and subtract those. And we're going to get negative 26/3. And, oh, we got to be careful. Negative 5 times positive 5/3 should be negative 25/3. So I'd be adding this to the other side. Be adding that to the other side. So be careful, that should be minus 25/3. And I'm going to add that to the other side. And then I'm going to divide both sides by 26/3, and x will be negative 1. So there's the negative 1 that we found earlier. So there's the negative 1 that we found earlier. Now that you know x equals negative 1, you can take that x value and you can plug it back into either of the equations. Plug it into either one, it doesn't matter. So again, I typically just plug it into the top one. Basically, I must just be because I'm not very creative, but I usually just plug it into the top one. So we're going to take that negative 1 and we're going to plug it in to, I'm going to plug it into the red equation. So 4 times negative 1 plus 3y equals 5. So that would be negative 4. I'm going to add it to the other side and get 9, and then divide by 3, and I get y equals 3, which is the solution that we got earlier. So my solution is still just the coordinate negative 1, 3. We already knew that because it's the same system we solved in the previous example. So you've seen the system solved using elimination and substitution, and both got us the same exact answer. So let's do this one more time, but by graphing it. So we're going to solve both of these equations for y, that way we can graph them. So same two equations, same system, we already know what the answer is, but let's see how we get that same answer by graphing it. So we want to solve both of these equations for y. So if I solve the top equation for y, you get y equals negative 4/3 x plus 5/3. So all I did was subtract 4x over to the other side and divide by 3. And then on the bottom, we get y equals 2/5 x plus 17/5. And again, all I did was subtract 2x from both sides and then divide everything by negative 5. So now that I have y equals for both of them, we want to graph these and see where they intersect. But to do this, we're going to use our graphing calculator. So graphing these by hand and trying to find their intersection point by graphing can be very tedious, and often, unless you're really careful when you graph, we only end up with an intersection point that's close to the one we're looking for. So if you are going to solve a system by graphing, we're pretty much just going to do that on the graphing calculator. Okay, so um, go ahead and if you don't have your graphing calculator out, go ahead and pause the video, get your graphing calculator out, and follow along. So I'm going to show you everything you would need to do to graph both of these and find their intersection point. Okay, so let's go ahead and graph both of these equations on our calculator. So turn your calculator on. If it's on the calculation screen, just go ahead and hit the button right below escape. So here's the escape button. Go ahead and hit the button right below it, and it'll switch it to the graphing portion of the calculator. At the bottom, let's go ahead and type in one of our equations. So it was negative 4/3 x plus 5/3 So negative 4/3 x plus 5/3, and then go ahead and hit enter to graph it. So it just graphed it on my calculator, graphed it blue. It doesn't really matter what color it does. And then let's go ahead and type in the other one now. So over here below, two buttons below the escape key, it says tab. So go ahead and hit tab, and it'll let you type in another equation. So it was 2/5 x plus 17/5. And then hit enter to graph it. And mine, it graphed it in red. And we want to know where they intersect. So if you look at the graph, these two graphs clearly do intersect each other at one point, and we want to know where that point is. Now we already know, because we solved this system twice before, that it's supposed to be -1, 3. So let's see how we figure that out using the calculator. So up on the top right of your calculator, there's a menu button. So hit menu, and then go down to where it says Analyze Graph. So Analyze Graph is right here. And then go down to where it says Intersection, and choose Intersection. And it asks for a lower bound. So move the little hand a little bit left of where you think they intersect. So we see that they intersect right here. So move the little hand a little bit left and hit enter. And then it says upper bound. So move the little hand a little bit to the right of where the intersection is and hit enter. And then voila, it shows you that they intersect at -1, 3. So that would be the solution to the system. So you just graph both of them on the calculator and have the calculator go find out what point it is that they intersect at to find the solution to that system. So this is an excellent way to check answers because the calculator can do this real fast. Of course, on homework or tests, I'm going to ask you to solve it by hand and show all your work, but this is an excellent way to check. And you know, keep in mind that they may intersect at like fractions or decimals, so the calculator may give you some decimals, so that could be an approximation of the intersection point. So the calculator is not perfect. It may not be able to get you the exact intersection point, but it'll get you close. It'll get you really, really close. Okay, so we graphed both these on the calculator, and we saw that they intersected at -1, 3. So I'm not going to draw a perfect graph here. I'm just going to do a quick sketch. But basically, we saw that one of the, we had one line and then the other line, and that they intersected right here at -1, 3, and that was our solution. So our solution, once again, because we already solved it, we knew the answer, was -1, 3. So again, we're just going to, basically, I just want you to understand that you could graph both lines and find where they intersect, and that would give you the solution. But we're not going to do that by hand. It takes too long, and the other two methods are a little bit quicker. The other two methods always get you an exact answer. So I just want you to be aware of this and to know that you can do it to check an answer if you have time. All right. So for this next example, I'm just going to say solve, and you can solve it however you want. So my personal preference, especially when I was your age in school, is I liked the elimination method. For me, that worked really well. But sometimes they'll give you a system where, like in this case, we have the top equations in standard form, and the second equation is already solved for y. So, some students would say, well, heck, it's already solved for y. Why don't I just plug that in to the first equation? So we can do that. So the bottom one is y equals negative 1 half x plus 4. So let's just take the top equation. And where there's a y, let's plug in negative 1 half x plus 4. And let's solve this for x. So we have x plus 2 times negative 1 half is negative 1. And then 2 times 4 is 8. X minus x is 0. So we get 8 equals 1, which last time I checked is not true. So that's false. So even though we're solving a system, just like when you were solving a regular equation at the beginning of the semester, if you get a false statement like this, there's no variables anymore, we just get a false statement, that tells us that there's no solution. So this system has no solution. So what that tells me is this is an inconsistent system because it has no solution. But the actual answer would be no solution. You just write down the fact that this thing has no solution. There is no coordinate x comma y that solves both of these equations. All right, let's solve this one. So this next one, we've got negative 3x plus 5y equals negative 6, and 6x minus 10y equals 12. So they're both in standard form. I'm going to solve this one using elimination. So I'm going to multiply the top equation by 2. I'm going to leave the bottom equation alone. And if I multiply the top by 2, I get negative 6x plus 10y equals negative 12. So when I add those together, negative 6x plus 6x is 0x, 10y plus negative 10y is 0y, and negative 12 plus 12 is 0. So I end up with 0 equals 0, which again, last time I checked, that's a true statement. So in this case, the variables disappeared and I was left with a true statement. So what that tells me is these two linear equations, if I graph them, they would be the same line. So the fact that I got a true statement with no variables tells me that the graph of these two equations would be the same line. So what this tells me is, so this means negative 3x plus 5y equals negative 6, and 6x minus 10y equals 12 are the same line. So any coordinate on the line solves this system. So our solution, we're going to write our solution, and it's going to look a little weird because we didn't write either of the other solutions this way, but the other examples we did either had no solution or they just had one coordinate that solved it. In this case, it's any coordinate on one of these lines that solves it. So here's what we're going to do. We're going to write it as a set. So it'll be the set of all coordinates x, y, such that, pick either equation. I'm just going to pick the first equation. No surprise there. Such that negative 3x plus 5y equals 6. So that's fancy speak that basically says any coordinate x comma y that solves this equation would be a solution to this system. So this is how we would write our solution set in a case like this, where if you graph both those equations, you get the exact same line. And you know that's going to happen if while you're solving it, all the variables disappear and you're left with a true statement.